Hello, welcome back. I'm John, old YouTuber. I got a break and was watching the Danish news 12 noon, but that's 2 hours ago. I did not finish downloading. I was reading the last one. Semiconductor devices fabrication. I'm not finished looking the document, but let's just try to continue what a wafer is, but I read it a long time ago, but I just like to get a break and go to also recording a lot of the Danish video. Actually, like this one, we have to put in the public. So let's put it public. And add it to my playlists. Good. And close my playlists. So let's read, then I can look this semiconductor devices PDF. I can look it later to find more PDF, but let's just read this. I need a minute to go to my bed. But now the camcorder had been charging 2 hours, but the camcorder takes like 24 hours to charging, so I will run out of powers in a few hours. To check my cell phone. Everything good. Let's continue. Wafer. I have read it a long time ago. Yes, I have the wire to my mouse. I have too little space on this small table. My papers fall on my floor.
Wafer, electronics. Top, polished 12 and 6 silicon wafers. Their crystallographic orientation is marked by notches and flat cuts, left. VLSI microcircuits fabricated on a 12-inch, 300mm, silicon wafer, before dicing and packaging, right. Bottom, solar wafers on the conveyor, left, and completed solar wafer, right. In electronics, a wafer, also called a slice or substrate, 1, is a thin slice of semiconductor, such as a crystalline silicon, Si, used for the fabrication of integrated circuits and, in photovoltaics, to manufacture solar cells. The wafer serves as the substrate for microelectronic devices built in and upon the wafer. It undergoes many microfabrication processes, such as doping, ion implantation, etching, thin film deposition of various materials, and photolithographic patterning. Finally, the individual microcircuits are separated by wafer dicing and packaged as an integrated circuit. History. In the semiconductor or silicon wafer industry, the term wafer appeared in the 1950s to describe a thin round slice of semiconductor material, typically germanium or silicon. Round shape comes from single crystal ingots usually produced using the Czochralski method. Silicon wafers were first introduced in the 1940s. 2, 3. By 1960, silicon wafers were being manufactured in the US by companies such as MEMC/Sun Edison. In 1965, American engineers Eric O. Ernst, Donald J. Hurd, and Gerard Seeley, while working under IBM, filed patent US 342362904 for the first high-capacity epitaxial apparatus. Silicon wafers are made by companies such as Sumiko, Shin-Etsu Chemical, 5, Hemlock Semiconductor Corporation and Siltronic. Production. Formation. The Czochralski method wafers are formed of highly pure, 6, nearly defect freezing or crystalline material, with a purity of 99.9999999%, 9N, or higher. 6. One process for forming crystalline wafers is known as the Czochralski method, invented by Polish chemist Jan Czochralski. In this process, a cylindrical ingot of high purity monocrystalline semiconductor, such as silicon or germanium, called a boule, is formed by pulling a seed crystal from a melt. 7, 8 donor impurity atoms, such as boron or phosphorus in the case of silicon, can be to the molten intrinsic material in precise amounts in order to dope the crystal, thus changing it into an extrinsic semiconductor of N-type or P-type. The boule is then sliced with a wafer saw, a type of wire saw, machined to improve flatness, chemically etched to remove crystal damage from machining steps, and finally polished to form wafers. 9. The size of wafers for photovoltaics is 100-200 mm square and the thickness is 100-500 m. 10. Electronics. Use wafer sizes from 100 to 450 mm diameter. The largest wafers made have a diameter of 450 mm, 11, but are not yet in general use. Cleaning, texturing and etching. Wafers are cleaned with weak acids to remove unwanted particles. There are several standard cleaning procedures to make sure the surface of a silicon wafer contains no contamination. One of the most effective methods is RCA clean. When used for solar cells, the wafers are textured to create a rough surface to increase surface area and so their efficiency. The generated PSG, phosphosilicate glass, is removed from the edge of the wafer in the etching. 12. Wafer properties. Standard wafer sizes. Silicon. Silicon wafers are available in a variety of diameters from 25.4 mm, 1 inch, to 300 mm, 11.8 inches. 13, 14. Semiconductor fabrication plants, colloquially known as fabs, are defined by the diameter of wafers that they are tooled to produce. The diameter has gradually increased to improve throughput and reduce cost with the current state-of-the-art fab using 300 mm, with a proposal to adopt 450 mm. 15, 16. Intel, TSMC, and Samsung were separately conducting research to the advent of 450 mm prototype research fabs, though serious hurdles remain. 17. 2-inch, 51 mm, 4-inch, 100 mm, 6-inch, 150 mm, and 8-inch, 200 mm. Wafers. Wafer size. Typical thickness are introduced. 13. Weight per wafer 100 mm to 10 mm. Die per wafer 1 inch, 25 mm, 19602 inch, 51 mm. 275 m 196,993 inch, 76 mm, 375 m 1972294 inch, 100 mm, 525 m 197,610 grams, 18, 564.9 inch, 125 mm, 625 m 198195150 mm, 5.9 inch, usually referred to as 6 inch, 675 m 198314420 mm, 7.9 inch, usually referred to as 8 inch, 725 m.199253 grams, 18. 269,300mm, 11.8 inch, usually referred to as 12 inch, 775. M2002125 grams, 18, 640,450mm, 17.7 inch, proposed, 19, 925 M342 grams, 18, 1490675mm, 26.6 in, theoretical, 20, unknown 3427. Wafers grown using materials other than silicon will have different thicknesses than a silicon wafer of the same diameter. Wafer thickness is determined by the mechanical strength of the material used. The wafer must be thick enough to support its own weight without cracking during handling. The tabulated thicknesses relate to when that process was introduced, and are not necessarily correct currently. For example, the IBM by CMOS 7WL process is on 8-inch wafers, but these are only 200 micrometers thick. The weight of the wafer goes up along with its thickness and diameter. Historical increases of wafer size. A unit of wafer fabrication step, such as an etch step, can produce more chips proportional to the increase in wafer area, while the cost of the unit fabrication step goes up more slowly than the wafer area. This was the cost basis for increasing wafer size. Conversion to 300mm wafers from 200mm wafers began in early 2000, and reduced the price per die for about 30–40%. 21. Larger diameter wafers allow for more die per wafer. Photovoltaic M1 wafer size, 156.75mm, is in the process of being phased out in China as of 2020. Various non-standard wafer sizes have arisen, so efforts to fully adopt the M10 standard, 182mm, are ongoing. Like other semiconductor fabrication processes, driving down costs has been the main driving factor for this attempted size increase, in spite of the differences in the manufacturing processes of different types of devices. Crystalline orientation. Diamond cubic crystal structure of a silicon unit cell flats can be used to denote doping and crystallographic orientation. Red represents material that has been removed. Wafers are grown from crystal having a regular crystal structure with silicon having a diamond cubic structure with a lattice spacing of 5.430710 A, 0.54300710 nm. 22. When cut into wafers, the surface is aligned in one of several relative directions known as crystal orientations. Orientation is defined by the Miller index with 100 or 111 faces being the most common for silicon. 22. Orientation is important since many of a single crystal's structural and electronic properties are highly anisotropic. Ion implantation depths depend on the wafer's crystal orientation, since each direction offers distinct paths for transport. 23. Wafer cleavage typically occurs only in a few well-defined directions. Scoring the wafer along cleavage planes allows it to be easily diced into individual chips, dies, so that the billions of individual circuit elements on an average wafer can be separated into many individual circuits. Crystallographic orientation notches. Wafers under 200mm diameter have flats cut into one or more sides indicating the crystallographic planes of the wafer, usually a 110 face. In earlier generation wafers, a pair of flats at different angles additionally conveyed the doping type. See illustration for conventions. Wafers of 200mm diameter and above use a single small notch to convey wafer orientation, with no visual indication of doping type. 450mm wafers are notchless, relying on a laser-scribed structure on the wafer surface for orientation. 24. Impurity doping. Silicon wafers are generally not 100% pure silicon, but are instead formed with an initial impurity doping concentration between 1013 and 1016 atoms per centimeter 3 of boron, phosphorus, arsenic, or antimony, which is added to the melt and defines the wafer as either bulk N-type or P-type. 25. However, compared with single crystal silicon's atomic density of 5,1022 atoms per centimeter 3, this still gives a purity greater than 99.9999%. The wafers can also be initially provided with some interstitial oxygen concentration. Carbon and metallic contamination are kept to a minimum. 26. Transition metals, in particular, must be kept below parts per billion concentrations for electronic applications. 27. 450 mm wafers. Challenges. There is considerable resistance to the 450 mm transition despite the possible productivity improvement because of concern about insufficient return on investment. 21. There are also issues related to increased into-die forward/edge-to-edge wafer variation and additional edge defects. 450 mm wafers are expected to cost 4 times as much as 300 mm wafers, and equipment costs are expected to rise by 20 to 50%. 28. Higher cost semiconductor fabrication equipment for larger wafers increases the cost of 450 mm fabs, semiconductor fabrication facilities or factories. Lithographer Chris Mack claimed in 2012 that the overall price per die for 450 mm wafers would be reduced by only 10-20% compared to 300 mm wafers, because over 50% of total wafer processing costs are lithography related. Converting to larger 450 mm wafers would reduce price per die only for process operations such as etch, where cost is related to wafer count, not wafer area. Cost for processes such as lithography is proportional to wafer area, and larger wafers would not reduce the lithography contribution to die cost. 29. Nikon planned to deliver 450 mm lithography equipment in 2015, with volume production in 2017. 30. 31. In November 2013, ASML paused development of 450 mm lithography equipment, citing uncertain timing of chip maker demand. 32. In 2012, a group consisting of New York State, SUNY Poly / College of Nanoscale Science and Engineering, CNSE, Intel, TSMC, Samsung, IBM, Global Foundries and Nikon companies has formed a public-private partnership called Global 450 mm Consortium, G450C, similar to Semitech, who made a 5-year plan, expiring in 2016, to develop a cost-effective wafer fabrication infrastructure, equipment prototypes and tools to enable coordinated industry transition to 450 mm wafer level. 33. 34. In the mid of 2014, CNSE has announced that it will reveal first fully patented 450 mm wafers at Semicon West. 35. In early 2017, the G450C began to dismantle its activities over 450 mm wafer research due to undisclosed reasons. 36. 37. 38. Various sources have speculated that demise of the group came after charges of bidrigging made against Alani Kaloyaris, who at the time was a chief executive at the SUNY Poly. 38. 37. 39. The industry realization of the fact that the 300 mm manufacturing optimization is more cheap than costly 450 mm transition may also have played a role. 38. The timeline for 450 mm has not been fixed. In 2012, It was expected that 450mm production would start in 2017, which never realized. 41. Mark Durkan, then CEO of